So in this last video, we provided a concrete example of how you would go about solving for how long it takes to return to a state. At this point, what I want to do, especially for those of you who are a little bit more mathematically inclined, is to generalize what we did here to work for any matrices, so you don't even, in fact, have to write out all these equations. You can solve the problem just by doing some matrix algebra. All right, so what I'm going to do is go ahead and erase all this stuff. All right, so again, we're not going to write out all these equations and all this stuff. What we're going to do is generalize how we solve for it. And so again, I'm going to kind of apologize here in that we're going to be introducing new terminology and new variables. But just keep in the back of the mind, usually the notation that we use is this mu ij. Right? And this mu ij goes by a few names, but what we're going to call it is, we can call it the expected passage time between state I and state j. Okay? So when I and j are the same, then we're talking about what is the expected passage time to return to state I, assuming we started at state I. All right. So what we're going to do in this video is walk through how do we solve for these passage times in a more general sense. So in order to do that, we're going to have to define a new variable. Right, and this is actually a standard notation, so we'll call it Fij. All right, and it is going to be the sum of n equals 1 to infinity of Fij n. All right. Now, what is this Fij and Fij n superscript? Well, this is going to be the probability of first passage. Between I and j in n steps. Okay, so it will be, what's the probability of going, let's say, from state 1 to state 5 in 3 steps? What's the probability of going from state 1 to state 5 in 4 steps, 5 steps, 6 steps, 7 steps? If we add up all those probabilities, this term here is in fact the probability of ever going from state I to state j. So based on this quantity, we can make 2 statements. All right. So if this term Fij is less than 1, that means there exists a probability that you are never able to go from I to j. Okay, so that would be sort of the case where, like, you know, maybe you have an absorbing node here. And we might ask, well, what's the probability of going from 1 to 2? Well, if you get stuck, or sorry, 1 to 3. If you get stuck in 2, right, then you can never get to 3, right? So with some probability, you're never able to actually get to 3. And if that happens, the expected time to get to 3 is actually infinity. Okay. So again, if Fij, so this is the probability of going from I to j, is less than 1, it is not certain that we ever it is not certain system will pass from I to j. And in fact, what this implies is that the passage time from I to j is infinity. So this is going to be one of the first definitions that we use. All right, so now let's say the probability of going from I to j, if we are to add up all these probabilities, was equal to 1. Okay, so this was the first case where we solved for the Fij's, and magically we're able to do that, and if it's less than 1, then we know the passage time is infinity. Alternatively, if Fij is equal to 1, that means we're guaranteed to, at some point, let's say if I'm unhappy, what's the probability that at some point in my life I become sad? Well, if that probability is 1, then it is certain the system will pass from I to j, right? And not only that, what we can calculate is, well, the mean passage time, this mu ij of going, the time it takes to go from I to j, is just equal to the sum of n times Fij to the n. And we're going to take that sum from 1 to infinity. Okay, so we're just saying, well, what's the probability of going from I to j in 1 step, 2 steps, 3 steps, 4 steps, and we're going to multiply times the number of steps. And so this is just sort of calculating our expected value, right? Yeah. So this is what we want to work towards. And so the question is, how do we even calculate that? Well, the way we go about doing it, so I'm going to mark this out. So I'm going to start right here, and then I'm going to erase a bunch of stuff. The way we go about doing it is we start by studying our first equation. So let's say, we're looking at this mu ij. We want to calculate the sum from 1 to infinity of n ij to the n. All right. So the way that we're going to do this is we're going to say, well, let's pretend. So here goes I, and here goes j. We're going to do a little trick where we're going to say, well, in order to calculate how long it takes to go from I to j, maybe we have to stop in some other state k first. Okay. And so if we were to assume that, what we'd say is, well, maybe we can go from I to j directly. So let's say this is a direct link from I to j, or we're going through some third state k. All right. So if we were to go from I to k directly, right, we can sort of do that. That then be the equivalent of pulling out the following sum. So we can say n equals 1 to 1 of n Fij to the n, okay? Now this is just 1, right? So n, because of this sum, it's just 1 and 1, right? But I'm just showing how we can split this up. Right. So in one step, we went directly from I to j. So I'm going to simplify that term a little bit later. All right. Now what we're going to do is say, well, kind of take that same process that we had done before, where we said, well, we're going to go through state K, and what we need to do is we're going to do one step to get to state K, and then we're going to ask, well, how long does it take, on average, to go from K to J? All right, so this is the same thing we did in the last video. It's just written a little bit differently. Okay. And so the way we go about doing that is we just say, well, that's equal to the summation of all the other states that we could visit that aren't J. Okay, because we said, well, we could go from I to J directly, or maybe we go to some third state K. Okay, so what we're going to do is we're going to look at all the possible states K that we could have gone through. All right. And so we're going to end up saying, well, it's going to take us one step to get to K. All right. And then we're going to be left with however long it takes on average to go from K to J. So we'll have mu kj. Now the only thing is, oops, and I shouldn't have written one. This isn't a probability one. This is the time step, that it was one step to go from I to K. Now what we need to figure out is, well, what's the probability that we even went from I to K? All right, so we're going to take this term and multiply it times pik. Yeah, all right, so you can see that. Cool. All right. So again, this is exactly what we had written before, but just in mathematical terms. So those equations that you had seen in the last video. All right. Okay. So if we focus in on this term, all right, so n is equal to 1. All right, so this is just equal to 1 times f of 1 ij. And so really what we're talking about is, what is the probability of going from I to j in one time step? Well, we already know that. That is just equal to pij from our one-step transition matrices. The next thing that we can do is we can look at this term here, right? And we can sort of multiply it out. So what we end up with is sum of k not equal to j. And I'm just going to put this pik inside of here. Pik plus mu kj times pik. All right. Now we can do a little bit of reorganization by recognizing, well, we're summing up over all the piks that are not equal to j, but then we have pij there. Right? And so in fact, we can take these two guys. So if you want to think about it, maybe one way we could think about it is, we're going to break this sum up into two parts. So we could write this as like, I don't know, the sum of pik, where k is equal to j. That's just this guy right here. And now I'm going to take this part out. It's the sum of k not equal to j of pik. And finally, we have this third sum, the sum of k not equal to j of mu kj times pik. All right. So the neat part is we can join these two summations, okay, because they're summing over pik, and this one has j, but this one doesn't have j. So in fact, that's the same thing as writing the sum over all states. So maybe if we have one state or infinity states, it doesn't matter. And we're going to sum over pik, right? Plus k not equal to j, mu kj times pik. Okay, so let's think about what's going on here. So I'm going to just draw an arbitrary, graph. Okay, so let's say we have 1, 2, and 3. If we look at just one of these nodes, let's look at 1, the probability that leaves 1 has to add up to probability 1, right? So like maybe this is, I don't know, 1/3. This can be 1/6. I think that would make that 1/2, maybe? Is that right? 3, 4, no. I'll just make my life easier. So 2/6, yeah, 3/6. Okay. All right, so the sum of these probabilities has to equal to 1. So anything, the probabilities leaving a node have to add up to 1, but that's exactly what we have here. We're saying let's sum up the probabilities over k, leaving node I. Right. What that means is this term right here, we can actually just rewrite as the number 1. Okay, cool. So ultimately, we're left with the following equation. All right, so we have, and again, this is all equal to mu ij. So if we move things around, we can say mu ij. So I'm going to move this term over, minus the sum of k not equal to j of mu kj times pik is equal to 1. And in fact, if you remember in the last video, this looks very similar to those set of linear equations that we had, right? Except in our case, I think we moved the variables over to the other side, and so we had a -1 instead of a +1, and we had a negative sign here, but a positive sign here. But again, it's sort of the same idea. Okay, so this equation holds true for all states j. And so what ends up happening is, just like in the prior video, we're going to end up with a system of equations. So what I'm going to go do now is actually write them out so you can kind of see and find the relationship to what we had before. So first, we're going to say, well, we kind of have to pick a j. Okay, so let's assume we picked a j. Okay, so maybe you want to know how long does it take to get to state number 10. Okay, and what we're going to do is we're going to say, well, let's write this equation out for I equals 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, or however many states that we have. So we'll write it for I equals 1, I equals 2, and we can also write it for I equals n, where n is the number of equations that we have. Okay, so let's sort of do this. So no matter what, we always have this mu ij. So So again, I'm going to write out the equation. So in this case, we have a mu 1j. Here we have mu, oops, that should be a 1, 2j, and we keep going down. We'll have a mu nj. So now, we know we're going to have to rewrite this summation. Okay, so we're going to go all through all the mu kj's times pik, where k is not equal to j. So what does that mean? So we're going to have, let's see. So let's assume j is not equal to 1. Okay, so j and I are not equal. Okay. Actually, we can. Actually, let's do this. Okay. All right. So let's do this. So for the first equation, we end up with mu 1j minus mu 1j times p11. Right? So that's just the first term here. We also end up with mu 2j times p12. And this pattern sort of repeats all the way until we get to k is equal to j. But we're not going to do that. So what we end up with is mu j minus 1 times p1 times j minus 1. Right? We're going to skip the case where k equals j. Right? Oops, I think there should be a j here. Right? We're next going to have minus mu j plus 1 going to j times p of 1 to j plus 1. Comma here. Okay. And then we continue on with the summation all the way to mu and j times p 1 to n. Okay? And again, all I'm doing is writing out this summation here. So we repeat this for the next line. Oh, in fact, I should have put a 1 here. Okay. All right. So for this next line, we have mu 1j times the probability that we go from state 2 to 1 minus mu 2j times the probability that we go from 2 to 2. And again, we're going to repeat this whole thing all the way to mu j minus 1 to j times p2 to j minus 1. We have mu j plus 1 to j times p2 to j plus 1. We subtract a whole bunch of stuff. Yeah. It's okay if you don't necessarily understand this, but again, I'm just writing out these equations just one by one. And in fact, this is what we had written previously, okay, in the last video. Except I just went through, we had numbers here that we could fill in very easily. Okay. So if we start at I, which is j, and we ask how long does it take for us to return? All right. So we have mu jj minus mu 1j times p j1 minus mu 2j times p J2. These are commas. Again, subtract a bunch of stuff. Pj to j minus 1. Pj to j plus 1. And again, we write a whole bunch of stuff in between. Okay, so we got this big ugly equation. And again, we do this n times for every single state that we have, which is what we did before. Pn 2, yeah. So we're sort of following the pattern, and I'm just being explicitly clear here. Hey, this is not fun. Okay. All right. So again, we've just written out every single equation in theory. This matches what we did in the last video. Now, nobody likes writing out all these equations. The big question is, can we just solve this using linear algebra? Well, we actually can, and it ends up being really, really nice. So let's sort of look at what's happening here. Oh, and again, all these are equal. So this is equal to 1. This is equal to 1. This is equal to 1. And this is equal to 1. Okay, so again, just from this equation. So our big question is, can we write this in the form ax is equal to some vector 1? All right, where we can just say, well, let's take the inverse of a and multiply it times a vector of 1s. So it ends up we can do that. And so if you look at what's happening here, sort of again, here our x is going to be equal to mu 1j, mu 2j, all the way down to mu nj. Okay. So let's sort of look at what's happening here. So we have all these mu ij's right there. So that's kind of like saying, well, we have an identity matrix times x. Right? Then we have all this stuff. Right? And again, we see these mu's in each equation. And what we're gonna do is we're going to say it looks like we're multiplying some funny matrix, and I'm just going to put a tilde over it, times x. Again, x contains all the mu's, and we're going to set that equal to 1, a vector of 1s. Okay, so I haven't defined what this n matrix is quite yet. Once you see it, you'll go, oh, that's really easy. But what we can do here is we can factor some stuff up. So we're going to have I minus n funny hat tilde times x equals 1. And so this is kind of the form that we want it in. And again, we have n equations with n unknowns. This matrix is going to be full rank. Right? So we can just say x is equal to I minus n tilde inverse times a vector of 1s. Okay, so what does this n matrix equal to? Well, if you look at what's going on here, it's just being multiplied. So our x, these mu ij's, are just being multiplied times p11, p12, p13, all the way through, except the only one we're not multiplying by is we're missing, in each case, let's get the red. You see how we jump from this j minus 1 to j plus 1, okay? So here we have minus 1, and then we go to a plus 1. And so what we're not multiplying by is times pij, or yeah, this column of p, we're not multiplying times the jth column, okay? And so what ends up happening is this n tilde almost looks exactly like our P matrix. So let's sort of work out what it is. So this n tilde and again, I'm going to pull out each of the terms here. So we see we multiply times P11 and P12. And we go all the way across to P1j minus 1. We skip P1j, so we just have a 0 there. We then have P1j plus 1. And we continue all the way to P1n. All right. So it ends up, we always multiply, kind of, P21, Pj1, Pn1. So we're going to multiply times all these. So we can go ahead and just write P21, P31, and this keeps happening all the way to Pn1. All right. Similarly, we're going to multiply times P22, P32, all the way down to N2. And this repeats all the way to P2j minus 1, P3j minus 1, down to Pnj minus 1. Now, in the jth column, we're going to have a bunch of zeros. Okay. And then we continue on with our P matrix where we have P2j plus 2, P3j plus 3. Oops, no, j plus 1. I don't know why I said that. All the way to Pnj plus 1. And then we continue with the rest of our P matrix. We're going to have P2n, P3n, Pnn. And so all we've done is taken our P matrix, okay, the transition matrix, and if we're saying how long does it take to get to state J, we find the column corresponding to state J and we just put a whole bunch of zeros in it. Okay? At that point, we can apply this equation in order to find the passage times. Okay, so let's actually do that. So I'm going to erase a bunch of stuff. And we'll do a simple example problem. All right, so I'll erase this guy so that you can sort of see what's going on. So let's say we had the following transition matrix: 0.3, 0.6, 0.1, 0.1, 0.6, 0.3, 0.05, 0.4, and 0.55. Okay, so one of the first things we might want to do is actually draw what this looks like. So we have states 1, 2, and 3. Point 3 loop back, point 6 go to 2, and point 1 goes to 3. For state 2, we have point 1, point 6, and point 3. Here we have point 0.05, point 4, and 0.55. Okay, so let's pretend my question was, I want to know the average time average passage time between all states and state 1. Okay? So I want to know how long it takes to go from 1 back to 1, how long it takes if you start at 2 to go to 1, and how long it takes if you start at 3 to go to 1. All right, so let's figure this out. So we have our P matrix, and what we're going to want to do is solve for this equation. All right, so here, I is just going to be the identity matrix of the same size as P. Okay. Now this N tilde, all we have to do is replace the column of the state we want to go to with 0. So in this case, we want to go to state 1. So what we're going to do is this column here, we're going to replace with a bunch of zeros. So when we do that, we end up with 0.6.1, 0, oh, I think I did this one. Yeah, 0.6.3, and finally 0.4.55. All right. So now that we have that, in order to calculate the passage time, so we're going to calculate the passage times from every state to state 1. That's going to be equal to n minus tilde inverse. All right. And we just have to multiply it times a bunch of 1s. Okay. And so you guys can go ahead and just do this in Octave or MATLAB. If you do this, what should your answers be? Actually, I'm going to go ahead and jump to Octave so you guys can see what I'm talking about and how we work it out. So again, just remember this, and I'll do the work in Octave so you can sort of follow along and do the same thing.